Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with excess and limiting reagents in stoichiometry. It starts on page 173 and it ends on page 177 from the text Chemistry 11 in Focus. And of course, deals with calculating limiting reagents and excess reagents in order to find the amount of products that are formed in a chemical reaction where you're provided with a certain amount of reactants. This is one of the concepts in grade 11 chemistry that students experience varying degrees of difficulty understanding. As this lesson progresses, you will see how this concept has been dissected in the most comprehensive way for students to have complete mastery of it. If you have the patience to listen attentively and follow all the explanations and illustrations provided, there will be no reason why you should not fully comprehend everything that is being said. What we'll do here, we'll use models of blue and orange ball to exemplify this concept and to bring about full understanding of how you go about finding limiting reagent and the excess reagent in a chemical reaction, because those two things are very important in finding the amount of products formed when two sets of reagents are mixed together. So let us say that orange balls and blue balls are the real reagents in a chemical reaction, and they are reacting with each other in a 1-to-1 mole ratio. So here you can see 1 mole of orange balls will react with 1 mole of blue balls to form a pair of blue-orange balls. Now let's say we have a problem where you're mixing two reagents. Let's say blue and orange balls represent these reagents, and you mix in 4 moles of one reagent that's represented by orange balls, and the other one that's represented by blue balls. Now as you look at that there, they're reacting in a 1-to-1 mole ratio. A number of things can be discerned here. How many moles of products are formed here? You can see that you have 3 moles of products here, because every 1 mole of blue balls will react with 1 mole of orange balls. So here you can see, because you have only 3 moles of blue balls, we end up with 3 moles of blue-orange balls, and 1 mole of orange balls is left in excess. In this case, let us say you're doing real chemical reactions, blue balls will be completely used up, and we'll call that the limiting reagent. Why it is called a limiting reagent? Because it puts a limit to the amount of products that can be formed. Doesn't matter how many more orange balls I put there, okay? I can have 1 million moles of orange balls. I will not get any more of these products here. Secondly, the limiting reagent also determines how much of the other reactant is being used up. So 3 things about the limiting reagent. 1, it is completely used up during a chemical reaction. And most importantly, it determines how much or how many moles of products are being formed. And thirdly, it can help you to determine how much of the other reagent is being used up. You can read the what I'm talking there about, all these things. Okay, same thing I've explained there to you. So we have 3 things about the limiting reagent. Listen to this one now. If in any chemical reaction it is told that one reagent is in excess, then the other one automatically becomes the limiting reagent, and it is completely used up. So look at this problem here. Here you have hydrochloric acid is reacting with sodium carbonate to give you water and carbon dioxide, right? Look, they're asking you this question. Use the equation there to calculate the mass of CO2 that is produced when that amount of sodium carbonate reacts with excess HCl. You're told that this one here is excess, and this one therefore becomes the limiting reagent. So what you do with this problem, you calculate the number of moles of your limiting reagent, and then you use that to find the amount of products. So as we established before, when you want to find the amount of products, you use the limiting reagent. So here's your equation. Now because you're being told that this guy is a limiting reagent, it becomes a given. You call that the given one. Now it's given to you. And now you require carbon dioxide here. Determine the limiting reagent. You're told that HCl is in excess. Therefore, this guy automatically becomes the limiting reagent. So next thing you do is to find number of moles of the limiting reagent. And number of moles, always when you want to indicate what you're finding, put this as a subscript there. And you use this formula here. Number of moles is equal to mass over molar mass. This is the mass, and this is the molar mass of sodium carbonate. So you end up having that number of moles of sodium carbonate, and that is given. Use the equation here. Now you know that this is given, and this is what is required. You can see the mole ratio here is 1 to 1. So the given to required is 1 to 1, here and here. And you know this is what is given. So the number of moles of carbon dioxide produced is equal to 0.2500 moles. And of course, knowing the moles, and using the formula here, you can find its molar mass, as done by this equation here. Number of moles times molar mass. You know in the formula, you can find the molar mass, which is this, right? So that is a mass of the carbon dioxide that's produced. We can have an extension to this problem now. They might want to ask you, what is the mass of the other products too? Water and sodium chloride. So you use the same understanding that you have there. We know that this was given to us. We've already calculated that. So you can use your limiting reagent to calculate any other thing in the equation here. Now this is establishing mole ratio here. 1 mole to 1 mole, 1 mole. You're using this to find sodium chloride now, okay? Look at the mole ratio now. This is 1. And this is 2. So the given is this, and you put the 1 up top. Now because you're finding this guy, he has a coefficient of 2, that comes to the bottom here. And you cross multiply. That's the number of moles of sodium chloride that is produced, okay? So you can find the mass of it. You multiply that by this using the equation, and that's the mass of your sodium chloride form. Now you can go ahead and find the mass of the water, same principle. In this case is 1 mole. Water is 1 mole now. So you do the same thing. You know the number of moles of your sodium carbonate, which is a limiting reagent there. That is the number of moles of water form. You have that is molar mass of water there, and this is the mass of the water. So these problems that are given here, okay, relate to that type of problem there where you're given one reagent and you're told that the other one is in excess, and you use that to find anything else in the equation. Now the real difficulty comes in when you're now given the masses of both reagents and you're asked to find the mass of a product that is formed. If you go back to our orange ball, blue ball pairing up, you can see again 1 mole of that reacts with 1 mole of that to give you 1 mole of. So you're given 4 moles of orange balls and 3 moles of blue balls, and you're asked now to find how many pairs or how many moles of blue orange balls. Here you can see again you only get 3 pairs here, or 3 moles. In this case, again, you say, what is the limiting reagent? Blue balls is the remaining, and orange balls are the excess reagent there. Again, doesn't matter how many moles of orange balls you have, you'll never be able to increase that unless you increase the number of blue balls. Let's look at a different scenario now. Let us look at it like this now. In this case, you have 4 moles of blue balls and 3 moles of orange balls. You have to find how many moles of, or how many pairs of blue-orange balls will form. In this case, what is the limiting reagent now? Orange balls becomes the limiting reagent, and blue balls can be said to be the excess reagent. And you get 3 pairs of these, or 3 moles of these, with 1 mole of blue balls left in excess. The only way you can get more of these is if you increase the number of what? Orange balls. If I put another orange ball here, then you end up with 1 more of these guys. See that? You end up with 1 more of these guys here. This will not be there anymore, and the reaction would have gone to completion. If you put another one of these now, then what will happen now? This becomes excess, right? That one becomes excess, and you have 1 more. So this is it in chemistry, involving real reagents, okay? You're not seeing balls anymore. You're not seeing balls that you can see and pair up nicely. Here you're given a reaction between sodium chloride and lead nitrate to give you a precipitate of lead 2 chloride. Here now is where difficulty arises. You want to know what mass of lead 2 chloride is produced when so this is our balance equation here. You're having 2 moles of sodium chloride reacting with 1 mole of lead 2 nitrate to give you 1 mole of lead 2 chloride. The first thing you will do is to find the number of moles of each of these 2 reactants here, using these masses here. Now that is the mass of sodium chloride, that is the mass of lead nitrate. Now if you want to find the number of moles, you take the mass, that's sodium chloride here, that mass, and this is the molar mass for sodium chloride. Let me point out something to you that students will do sometimes. When they do this division here, because they're seeing a 2 here, listen to this. This is what they'll do when they want to find the molar mass. They will double, they will take twice the molar mass of sodium chloride, which is erroneous. You do not do that. These coefficients here are used to establish mole ratios. Doesn't necessarily mean if you have a 2 there, you have to double what this is. Okay, so just find the molar mass of sodium chloride and divide by that, all right? Which is done correctly here and not like what you have there. Now you go and you find the number of moles for lead 2 nitrate. That is the mass of lead 2 nitrate, and you end up with this value here. You're having the number of moles of both reagents, right? The next big step, which is the one that students find difficult to do, is to find the limiting reagent. Now you're introducing a different terminology here, experimental value. Okay, listen to this now. This is what is happening. 1 mole of this is reacting 1 mole of that to give you 1 mole of blue-orange pairs. If I have in a real reaction, where I'm mixing reagents, 4 moles of one reagent, that's 4 moles there, with 3 moles of another reagent, as represented by these different colored balls, I'm going to call that my experimental value. That is what you're actually using in the experiment, okay? According to this now, you can have a little prelude of what we were doing. According to this, what you're seeing here, you can ascertain which one will be the limiting reagent and which is going to be the excess reagent. Because you're dealing with balls, you can see that 3 of these will react exactly with 3 of these here, and therefore blue balls will be in reagent and orange balls will be the excess reagent. But this is not how it happens. You can't see that so nicely when you're using raw chemicals, right? So let's go back to this one again. In that illustration that I showed you there, you're using 4 moles of orange balls. We'll call that the experimental value. In theory, for all of these to be completely reacted upon, I would have needed 4 moles of blue balls. So we call that a theoretical value, okay? But look, in the experiment, I only use 3 moles of blue balls. So what can we determine? We can determine that the amount of blue balls was less than what was required. This is less than what was required. And therefore we can say that this is a limiting reagent and that guy there was the excess reagent. All right? So this is what we'll do. When we do real problems, we're going to put the number of moles of the 2 reagents that are used in the experiment, put them next to each other, line them up next to each other, and we can make the deductions that we did here just now between what is required and what was actually used in the experiment, and that will help us to determine which reagent is in excess or which is limiting. Another student now might want to use blue balls to try to find how many orange balls are required. Here you have an experimental value for blue balls. In theory, you'll need 3 moles of that. Now, when you see what is used in the experiment, you'll find out that you're using an extra mole of orange balls, so you conclude that that guy is in excess. As long as this guy is in excess, this one here automatically becomes the limiting reagent. All right, let's go on and do a real problem. So you see, it doesn't matter which reagent was used first. The final result will all be the same. Everybody will conclude in this case that the blue balls or the limiting reagent. So go back to that problem now. If you go back to that problem with being lead 2 nitrate and sodium chloride to find how much PB is formed, we already calculated these. We change them to moles, okay? So go back to our equation now. 2 pathways of finding the reagent. Pathway A. When I give problems like this one here to my students, some students will choose one reagent. Like in this case, they'll choose lead 2 nitrate to see how much of this guy was supposed to react with it. Some other student will choose this one here to see how much of that one is used to react with it. In both sets of students, they'll end up with the same limiting reagent. But I'm going to do that to show you how different students will approach this, and they'll end up with the same result. Now we'll choose number of moles of lead nitrate to find out in theory whether or not this value here is correct, whether you need more or less. Okay? So because you're choosing this one, it becomes the given quantity, and this one here becomes the required quantity, right? So set up our mole ratio here. The given one is, of course, the mole ratio is 1, and that is 2. So the given one is 1, and the required one is 2. Put in the value there for the given one, and X now, which is the number of moles of sodium chloride that it's supposed to use, is this value. So in theory, you're supposed to use that number of moles of sodium chloride. But in the experiment, that's what we calculated there, see? In theory, we're supposed to use 0.100 moles of sodium chloride to react with that amount of lead. But we use less. This value is less than that. So that is how much you're supposed to use to react with that amount of lead. But you only use this. Therefore, this one here is going to be completely used up, and your lead here is going to be left in excess. So let's see what we wrote here. Comparing the experimental and theoretical values show that the amount of NaCl used in the experiment, this, is less than what is theoretically required to react with that amount of lead, and it can be concluded that NaCl is the limiting reagent. So note this then. If the experimental value of a reagent we're using the experiment is less than what is theoretically required to react with the other reagent, this is less than this to react is this, it becomes the limiting reagent. Let's see what another student will do, and you probably will do that, and your friend will do that one day before. Now you're going to choose now. We just want to show you how you end up with the serum. You're going to choose this guy here to find how much of that guy is required. So this becomes a given reagent, and the other one becomes required. So you choose that one there. Now if you choose sodium chloride from the equation you can see now the number of moles is 2 to 1. When you chose this one, this was 1 to 2. Now you're choosing the other one, become 2 to 1. 2 to 1, and that's the number of moles of sodium chloride. And you end up with that amount of lead nitrate that was supposed to be used. This, I can divide by 2. Divide this by 2. This is what was supposed to be used. Alright? Don't worry with this now. So you're supposed to use that amount of lead. But look, you use twice the amount in the reaction. Alright? So in this case, what are you going to say? Lead becomes the what? Excess reagent. And again, sodium chloride is a limiting reagent because it is used up. So this is it. If the experimental value is more than what is theoretically required to react completely with the other one, it becomes the excess. As in this case here, lead here is the excess reagent because you only needed that amount of lead in the reaction, but you use that amount there, so it becomes the excess reagent. Now this next part, you find amongst the protein. Use a limiting reagent here, which is become the given reagent. That's a limiting reagent, and you want to find that, okay? The mole ratio is 2 to 1, and this is the number of moles that you use in the experiment. So when you're using the limiting reagent, use the number of moles actually used in the experiment to find the products. In this case, it will be this number of moles of PbCl2, all right? And you end up with that amount. You can have an extension of the problem. We're asked to find this mass here, so what are you going to do? You use a limiting reagent, maybe 2 to 2, 2 moles to 2 moles. Same mass you'll use here, same number of moles here, okay? Then you're going to do this one here, and you find the number of moles of sodium nitrate, see? That now becomes the required one. And then you end up with that number of moles of sodium nitrate. This is the molar mass of sodium nitrate there, and you find that. Again, because you have a 2 here, because there's a 2 here, okay? Students are going to double up the molar mass. Now this is the correct molar mass, not this one here, okay? All right. We'll do one more. We'll do one more problem, and hopefully when you finish this one here, everything becomes clear again, okay? So we have magnesium reacting with hydrochloric acid. These are the real masses that you're using. When you say 6.3 grams of aqueous hydrochloric acid, we mean you're not including the water. That's the real mass of the hydrochloric acid that's dissolved inside. That goes to any aqueous compound. So this is a balance equation here, okay? 1 mole to 2 moles give me 1 mole here and 1 mole here. Okay, just relax, and we do the same thing again one more time. All right. So what do we do? You have to find the number of moles of each of the reactants. We end up with that number of moles of magnesium. We call that the experimental value because we're using that in the experiment. Okay? Doesn't mean that these are the correct values, right? This is the number of moles of HCl. You know how to do that already. And we call this again the experimental value. One of these here is in excess and the other one is limited. Or what could happen, it could be exactly the same number of moles that are required. In this case, both of them will become the limiting reagent. If you use correct amounts, you can use any one of those here to find the products, right? But in most cases, you just mix things arbitrarily, and then you ask to find the mass of a product, then the problem becomes difficult. So we'll show you both ways the students will avoid the limiting reagent. Choose the number of HCl, okay? So HCl now becomes your given reagent, and you want to find the number of moles of this that's required to react with that number of moles of HCl. Your mole ratio is 2:1, and here you're going to find that this is the amount of magnesium in theory that is required to react with that number of moles of HCl. But look, in the experiment, that is the number of moles of magnesium you've used. We calculated that. Ask yourself now, did I use enough? Did I use more or less? I should have used only that, but I used 10 times more. So what are you going to say? What are you going to say? This guy here is the excess reagent. Okay? So let's read here. When you compare these two values, we see that the amount of magnesium used, that is more than what is required to react with that amount of HCl. Only that amount was required, but you used that. In this case, all the HCl will be used up, and it thus becomes the limiting reagent. And of course, magnesium is the excess reagent. Let's look at it from a different angle, a different student now. A different student might now choose a number of moles of magnesium now to find out the moles of HCl that can react with it completely. Okay, in this case, the magnesium they're choosing there becomes the given reagent, and the other one becomes the required reagent. So now, let's look at it. You're choosing magnesium, and of course, you remember we calculate that's the number of moles of magnesium we use. Now magnesium is only 1 mole against 2 moles of HCl. The 1 mole is in line with that. You have 2 moles there. And it turns out that this is what you're supposed to use. That is the amount of HCl that you're supposed to use to react with the amount of magnesium. So look what happens. You were supposed to use that. Look what happens there. You use 10 times less. So here again, you can see all the HCl we used up, and you call it the limiting reagent again. So here again, when you compare these two values, you can see that the amount of HCl used in the experiment, this one here, is less than what is required to react with that number of moles of magnesium. We conclude again that HCl is a limiting reagent. So both sets of students will be correct. Now you use your limiting reagent to calculate what you're asked to do. You're asked to find what mass of hydrogen is produced when you react those quantities of magnesium and HCl. So now use your limiting reagent. That becomes the given reagent. I can see 2:1 mole ratio. So given over required is 2:1. Put in what you actually use. These values here are actually used in the experiment, not what you're supposed to use. So you find that That is the number of moles of hydrogen that can be produced. And of course, watch me now. You see how you have this H2 now? You have to double that. I did allude to that sometime. When you have H in a compound, it's going to be 1.01 gram per mole. But when it is produced, it produces molecules, right? And therefore, you have to use the molar mass of molecules there, and that is what you have there. Okay? Go through these problems again, listen to it attentively, and then I'm sure you're going to understand what we're doing. It's a little bit painstaking. I try my best to dissect it as much as possible, that you have full understanding of that. There's something called percentage yield. Okay. You expected that amount of hydrogen, right? That amount there, okay? But sometimes someone to collect that hydrogen and weigh it, because of experimental errors, sometimes you don't get exactly what you expect or what was expected. We got this, well, we expected this. So percentage yield, take the actual amount over the expected amount and you multiply by 100, and that gives you the yield. Let us say in the problem above, you expected to get that amount of lead chloride, lead 2 chloride, but you only got that. Let's say you precipitate that and you filter it, you dry it, and then you weigh the precipitate, and you got this, okay? Percentage yield will be equal to actually get over this guy here times 100%, 94%. If you can use this problem before here, you're having a certain mass of magnesium reacting with a certain mass of HCl, and you're asked to find the mass of H hydrogen that is produced. What did he say? First of all, you change these, find number of moles of each, and you call these the experimental values. Right? Then you choose one to find how much of the other is supposed to react with it completely. So in this case, we chose hydrochloric acid to see how much of this guy was supposed to react with it. This is the amount of hydrochloric acid in the experiment. This is the amount now of magnesium that was supposed to react with that amount of hydrochloric acid. But in the experiment, we use that amount of magnesium. Here you can see that we're using more magnesium. In theory, you're only supposed to use this, but in practice, you use that. So in this case, you can see the magnesium is more than what is required, and therefore it will react with all the HCl there, and some of it will be left in excess. So the HCl is the limiting reagent, and magnesium. Another student doing the same thing, I'm not going to go through that, will also end up with the same conclusion that the HCl is a limiting reagent. Now you use your limiting reagent, the one you actually use in the experiment, right? This value, right? That's what you actually use, okay? To find how much of the product is produced. So this becomes the given reagent. You have 2 to 1, establish that mole ratio there. And you find that is the number of moles of H2 that is produced. You have to use the molar mass for H2 gas, which is 2.02 grams per mole, and that's what is it. The percentage yield is what you actually get over what you expected, and I give you 2 examples there, and that's what it is. And it's a summary here. Can go through the summary. I did one with solutions there. You haven't done that yet, so you can go through that for your own curiosity and see what is happening there. I haven't taught you that. We'll do that later on. But you're reacting that amount of sodium hydroxide with that amount of sulfuric acid. I haven't done solutions yet, but if you want to watch that, see if you done, if you did this course and you want to review that, no problem. And there's some summary statements here. You can follow that. All right. All right. And of course, at the end of all these units, chapters and so on, there are a series of questions for you to do. All right. A series of questions. There are lots of multiple choice questions, true or false. All of these are restated in the solution manual. Answers are there, solutions are there. Okay? To help you. I hope that was helpful. I'll see you again